Welcome to the community panel at the Fully Connected conference presented by Weights and Biases. My name is Corey Strassman, and I'm a community manager. I'm excited to spotlight two members of our community, Andrada and Atharva, who will be presenting on today's topic, Built with W&B. As we continue to grow, you will see a lot of focus on the most successful part of W&B, you. We'd love to capture what you have utilized W&B to build and provide a platform for your ML practice. Today, I'm excited to introduce our panelists who have accomplished so much with Weights and Biases. First, Andrada is a data scientist at Andrada, a W&B dev expert, Kaggle Notebooks Grandmaster, and Zibi HP Global Data Science Ambassador. Andrada, welcome.
Thank you, Corey, so much for the introduction. I'm super happy and grateful to be with you today. So before getting started, a little bit of a backstory. So when I started doing data science and I was starting to do experiments, I didn't even know at that time these are called experiments. And I remember I was doing, the melanoma competition on Kaggle a couple of years ago. And I was experimenting with efficient nets and epoch sizes and batch sizes. And it was super, super, super fun. And I was keeping all the outputs, the recording of all the outputs and the results in my notebook. And I had pages of changes or little tweaks that I was doing, and I was writing them down. And of course, at some point, I kept track of some information, or some information was lost in the process, and it was quite hectic. It was fun, but it was super hectic. And I didn't know actually there is a smart way to keep track of everything that I was doing instead of, just writing on hard paper. And then I discovered Weights and Biases. And at this point, every time I'm doing anything, I am using Weights and Biases because it's extremely, extremely easy and seamless. And it goes right in the code. It's not very complicated. I swear to God, I'm sorry to say, but at the beginning, I really thought, this is going to be so complicated. How do I implement this in my already existing code? It's not. It's just very, very simple lines of code. And in like 4 or 5 lines of code, you are already set and good to go. And you are tracking everything and you are saving everything. All the your artifacts or your models or the versions of your data sets that you're preprocessing. So it's super, super, super easy. And now my folders don't look so hectic anymore. So anyways, today I am going to present to you a project I did on Kaggle a few months ago on RSNA fracture detection competition. So very quickly, what we had to do, we had these DCOM files and a metadata of those DCOM files that contain CT scans of the cervical spine, or the part of the human, this the cervical spine. And we had to identify in which vertebrae, or if in any vertebrae, there was a fracture. There can be multiple fractures in one patient, or there can be no fractures in one patient. So this was the idea. So first, I did the exploratory data analysis and the preprocessing, which I really, really, truly love. And this is the part that actually excites me the most. So here, very simply, you import Weights and Biases, and you can forget it. And then you log in the secret key. Usually, if you are in your notebooks, you just have an API key that's in your profile and you use it. But because this notebook is public, I am using Kaggle secrets. But it's just a line of code when you say 1DB login and then your unique API key. And because I've been using Weights and Biases for so long, and at some point my code started to be repetitive throughout my notebooks in terms of what I wanted to do. Because for some example, I wanted to save plots, and saving multiple plots kind of got me repetitive code, or save artifacts. I did these very quick and easy functions that I just call. And they save my artifacts for me. And here my plots, I have here an argument that says line if I want a line plot, a bar if I want a bar plot, and a scatter if I want a scatter plot, and so on. Okay, so first I started looking at the tabular data. Here is my first experiment. It's super quick and easy. And this creates here, let's find out. So Tabular Explorer, I have here Tabular Explorer. Usually within my dashboard, so this is my dashboard for this composition. I immediately, once I create the dashboard and I start logging things into it, I come here and group by name. Because if you don't group by name, the experiments are going to come up as you run them. And as you can see, there are quite a lot of experiments for this particular project. So immediately, no question asked, I come here and I put name and I have everything here. And it's kind of grouped. So I don't have to, mess around or search for a particular experiment that I'm looking at. Okay, and then here I'm reading the data, I am looking at the CSV files, and here I'm beginning the analysis. I'm doing, for example, some bar charts. So what I find extremely interesting and very, very useful is sometimes when you are having a big project, and here is not the case, but sometimes you have 5, 10, even tens of CSV files or just tabular data sets that you are looking at. And you are finding some very, very interesting information that you want to keep, like a graph, for example, that you want to look at in the future. In this case, I would highly recommend, like I am doing, is to log all the bar plots or the charts that are very, very interesting to you into the dashboard. Because in 1 month, when you come back to the project, or maybe you want to look back in the past, it's going to be super, super easy instead of just looking between notebooks and notebooks to find that information. So this is why, for example, here, I have this graph where I see, okay, the patient, I can see the labels are 50-50. So I have 50% of my patients that had no fracture, and 50% of the patients had at least one fracture within their cervical spine. And here I have also the information on which vertebrae within the 7 vertebrae within the cervical spine had fractures. So most of the fractures, for example, were in the first vertebrae, whereas the least fractures were in the last vertebrae. And this is very, very useful information for you or for your teammates, because you can share this dashboard with your teammates. So save anything or any number that you might find useful or interesting or just useful in the future. Okay, so here I'm doing more exploration just to understand. Here I'm also saving the images just to have an understanding within the dashboard, which is super, super, super easy. I just log using 1db.image, and then here I have all my images within the notebook, but I also have my images within the dashboard, which are right here. And if I can look a little bit through this, you can see how they change as the CT scans evolve for this particular patient, which is very unique and weird number. Okay, so I'm going through some example. Then I am looking at the DCOM metadata. If you might not know, within a DCOM file, this is just a format how they store these medical images. They store some additional information like the image position, how the certain camera or whatever is called in the medical field was the position of it when they took the scan. So a lot of information. So here I'm saving all this metadata. I am logging this information within my dashboard. And then I'm looking at it to see some distributions, saving them to weights and biases as I find them interesting, or if I find them interesting, and so on and so forth. Okay, now here I'm looking at some bounding boxes, because so it wasn't only the fact that the CT scans are or are they not within the image, but we also had the information of the placement where the structure was at. And I kind of wanted to look at that too. And I think that's about it. Here I looked at the 3D scan, and then here I'm saving my artifacts. First, the training data. that I pre-processed from the competitors, from the competition. And then the second was the metadata from the decomp file. Okay, now the second notebook was just a very baseline model that I used to train and kind of try to inference whether there was fracture or not within the cervical spine. Okay, so it's exactly the same procedure. We import weights biases. Here are some other libraries that I use. Import my API key. Here again, I do this all the time. Even if I'm not using it, I'm doing it because you never know. My two trusted functions to plot and save my artifacts. And then I started looking at the evaluation metric because usually, you have one target within a competition. In this case, there were 8 targets. So one target flagging if the patient had any fracture, and then the other 7 targets with 0 if in that particular cervical area there was a fracture, and with 1 if it wasn't, and if 1 if it was a fracture. So there were 8 targets in total, which was quite interesting. So the evaluation metric was a little bit interesting, or I haven't seen something like this before. There was a custom loss function for this competition, and here is just the normal drill. I'm doing a data split. I'm creating the PyTorch data set to read in the metadata and the images. Here is the model, the loss, and the gradual warm-up, and then we're going into the training part. So here, first is the training function, the training for one particular epoch, so just for one epoch. And just logging in to weights and biases, all the metrics that you want during training, it's super, super easy. So once you usually go through model.train, and then you loop through all the batches and do all the forward and backwards propagation, you compute the losses. And then everything I did here was to log into weights and biases with 1db.log, the train loss, and then the competition loss. And then that's it. And then I add step equals epoch. So every epoch, one weights and biases logs this information for me. And then for the validation epoch, it's exactly the same. So at the end here, I log the validation loss, the validation competition loss, and then one more step, I added here the validation area under the curve, which was just another metric that I wanted to use in this competition. So you can log whatever and how many metrics you want for each epoch. Okay, here is a very cutesy scheme, let's say, of how the full training pipeline works. And here with the spiky yellow is wherever I'm using weights and biases. So I'm using weights and biases only in 3 places. And then I run everything, and it's super easy, and it keeps all the information that I want and that I need. So at the beginning, and then when I'm doing the training and the validation, and that's it. So at the beginning of the training, like the big main training function, I am creating my configuration for this particular training or an experiment. Let's say I am creating my parameters. Here you can put how many parameters you want. Here I am explaining, okay, so my model is a dense net. Here I'm inputting all my epochs, the split, the k-fold validation that I used, the batch, the learning rate, how big or what was the size of the images, the stack size, and the data frame size. And then I update my parameters. So run config has my parameters. Then I create the experiment, and then I go through the steps that you would usually go. Here I track my model and the guidance of my model, 1db.watch, with a frequency of 100, so you don't overclutter everything. And then I am training. Here are my training and my validation functions that I showed you previously. And then once everything is done, I just do 1db.finish, and everything is stored within your dashboard for you, for your teammates to see. And it's extremely easy to also compare between experiments to see for how long they have run, also if they plateaued in some point, what was the point, and so on and so forth. So here I'm actually doing the training. It trained for a while. And then lastly, at the end, I'm saving two artifacts. So first of all, it's the logs. So during the training, I also logged some information that I wanted into a TXT file, which I saved. I actually can show you here. So within the artifacts, I have here logs, which has two versions. And in files, I have it here, so I can download it at any time if I want to. But that's the thing, you don't have to overclutter your device with a bunch of folders having data, 100 TXTs for 100 experiments. You have just everything in your dashboard, and if you want to look at something, you can just download it. And then I have the actual model. So within my special function, this is super easy. Anybody can do this. I have a data type for dataset. If I have anything like a CSV or a Parquet file or a TXT file, and then for a model, if I have a trained model that I want to save. And here, for example, I have my model again with the version 1 and version 2, and then here is the file. Okay. So yeah, I hope you liked it, and thank you so very much. And I hope you will try this in the future. Thank you.
Thank you, Andrada. Thank you for this interesting use case. I'd like to introduce our next presenter, Atharva. Atharva is currently in the last semester of university. He's an intern at Wolters Kluwer, and his work mostly involves document intelligence. Atharva has been an active W&B user for the past 3 years, and is also one of our ambassadors. He's very active in Kaggle competitions, is a Kaggle competition expert, and is avidly involved in open-sourced contributions. Welcome, Atharva.
Thank you, Corey, for the nice introduction. Thank you for having me. So today I'm going to talk about 3D segmentation with Monai and PyTorch with weights and biases integrated inside of it. The Monai library, as many of you might not know, that NVIDIA is the co-founder of the project Monai, and it is a PyTorch-based framework which you can use for your imaging data or any medical kind of problem statement that you may have. Monai has all of the things that you might need in any medical project. So it is completely open source. Anyone can use it, and anyone can even see the code and contribute to it. So for this talk, I'm going to talk about segmentation of spleen. So many of you might not know what a spleen is. Basically, spleen is an organ which is located beside your stomach, and its main responsibility is to clean your blood cells or kill the unused blood cells, etc. So the data is from medicaldecathlon.com. There are many tasks inside of it, like lung segmentation, brain tumor segmentation. So I've just picked up the spleen. So here I'm just installing Monai, weights and biases, matplotlib, all the necessary stuff. Then I'm downloading the data here. I'm downloading the spleen dataset, and the spleen dataset comes in 3D volumes. So this particular dataset had 61 images inside of it, 41 for training and 20 for testing. And the 3D images are arranged in such a way that each image, so for in each 3D image, we have multiple 2D images. So these are splices of that 3D image, and when we combine them in 3 dimension, they form the complete 3D volume, and we can see the whole 3D structure of the image. So this is a segmentation task, and for any segmentation task, it is important to look how the segmentations are drawn on the image, how they would look on the image actually, or the ground truths that you're dealing with. So I'm just defining a utility function to log the weights and biases log the image on weights and biases dashboard along with the mask data and the class label. So 0 is for background and 1 is for the mask. We will see that shortly below. So I'm just logging a single image or some splices from a single images. And so I've just set 100 splices from a 3D volume. So we can see that this is index 0 is basically the slice 1, slice number 0. Then as you can go further, then slice 10, slice 15. So this all the slices combine a image. And then we can see the segmentation mask here. So we can see that these red thing that is being masked here is the spleen organ we are dealing with. Yeah, and the 3D image start from left. So let's say you are starting from the start, then you are not seeing any spleen organ here. But as you progress further, you might see the spleen organ because it is in between the, as you can see, these red markings are, so basically the between part is being showed here, and then after that we see that there's no like the segmentation mask. So we understand that the spleen is basically located inside the 3D volume and inner part of the 3D volume. So yeah, moving further, then I'm defining the configuration in a dictionary format here. So weights and biases allow you to track every thing you are doing. So you just have to format in a way that it can be later serialized into a dictionary format so that the weights and biases can accept that in the W&B.init method. And as you can see, this is my cache rate, number of workers I'm using, train batch size, validation batch size, learning rate, etc. Everything is being tracked on weights and biases. And for this task, we are using dice metric, which is a common metric used for segmentation. And I will quickly run you through the training process, how you can log your losses, all the gradients, all the validation losses, accuracies, etc. So we start weights and biases run with W&B.init method. Now you define the project, and W&B.init accepts many arguments. You can look up on the documentation. So it accepts things like tags, which you can use for filtering the runs. Then things like nodes, which you can keep a track of what you were doing at the time of running the experiment. Then I'm just using W&B.watch to log the gradients of the model, and I've set log frequency to 100. So it will log after every 100 steps or 100 batches. Then this is a typical PyTorch training loop, which I won't explain in depth. So this is the main where all the losses are being tracked. So just with a single line, you can see what are the losses, what was the loss, how the loss progressed over the training period. So, and W&B.log is a very powerful method. You can log anything, ranging it from scalar values or text. Even you can log 3D objects, you can log images. So anything you can think of can be logged using W&B.log. Then I'm also logging training loss for each epoch. Here I was logging for per step, here for each epoch. Then one of the main thing I log is learning rate, because if you are using a cosine scheduler with warm up, and if your learning rate is not behaving as per you set for some reason or some error input, you might never know, because it will not throw any error, right? So now basically you have to log the learning rate. It is a very important practice to log the learning rate, so that you know that there are no silent errors in your code, and your whole the learning rate situation is being taken care of. Then I'm also logging the dice metric here, which is the main thing we are interested in, the validation dice metric. Then also I'm saving the model, the best model after each epoch. So if the model improves after each epoch, I'm saving it as in a PyTorch typical.pth file. Then at the end of the run, I'm saving what was the best dice metric, what was the best metric epoch, where I got the best dice metric at the end of the run. So here you can see all the losses being plotted here. So I will quickly show you this in the dashboard itself. So these are all the runs that I've run or being experimented with, and these are all the plots you can see. So this is train loss which was being logged after each step. This was the loss which was being logged after each epoch. And as I say that sometimes I used a no learning rate decay, sometimes I used a cosine decay. So you can clearly see how the logging the learning rate was useful here. And we can see the dice metric. Also, it's very helpful if you plot a scalar chart, which will show what was the best experiment you ran. This is a W&B scalar chart, which shows that Glorious Donkey 58 was my best experiment with a validation metric of 0.9527. And moving further to the gradient section, like logging the gradient section. So it is very important to know what the gradients of the model are across the training period. So with just a single line of command, you can log all the model gradients, and you can see the gradient of each layer. So how to interpret this graph is like if first this is basically a histogram, and you might see for each layer the histogram, that is the distribution of the histogram should come towards 0. So as you can see in this gradient charts, the at the later ending stage of the run or any experiment, the chart should be centered at 0, so that the model has reached the global optimum, and there's no gradient update performing. And then also you can see the system metrics like GPU utilization, all the temperature. So it is very important that you use your GPU to the fullest, and you use your hardware to the fullest so that there's no blockage. And the main another thing is versioning models. Weights and biases also provide a way to, so we saw how to version your experiment, or how to track the experiment, but weights and biases also provides versioning your models or data sets. So for each experiment, I was versioning the model and using the want.artifact command. So you can version your data sets or even models using this command. And I'll quickly show you the artifact. Yeah. So as you can see, it creates for each run a version of the artifact or version of the model, and you can just download it using this small code snippet that weights and biases already provide. You can see useful information like what was this model name. You can even set aliases to the model so that it becomes easy for you to filter out or download anything. Then you can see the metadata, all the configuration that was used to train this model, then all the files. So suppose in artifacts you might have many files. Here we have only one, but there can be many files in this. And we can even see the lineage, so from which run the artifact came. And then if we use this artifact in another run, you can also see this in this tab itself. Then moving to the, you can see the predictions in table format as well, or the configuration in the table format as well. So you can see all the things we have passed in the W&B.init in the config parameter. All of these things are being showed here. Then we can log. So one of the favorite features of weights and biases is tables for me. So it allows for error analysis. You can see where your model is doing wrong, so you can improve on that model. So weights and biases provide W&B table, which you can use to log arbitrary data in a table format. So you can group by certain things, or you can filter. You can do pretty much anything you can think of in a tabular format. So yeah, I'm just logging some sample files, sample predictions from my model. And we can see in this table that this is the file name, and this is the image that was used, and this was the ground truth mask, ground truth segmentation mask, and this was the prediction. So we can see that almost ground truth prediction matches our ground truth. So our model is doing well in segmenting splints by now. One more modification any user or anyone can do is also logging the loss for each of the images or each of the predictions. So you can sort by ascending or descending to know which on which image the model has the maximum loss. So you can just filter out based on that to improve on the model. Then you can even compare two runs in a single table using the join feature in the tables itself. So for this image, we can see that this zeroth run was kind on 65 and one index run is a leafy dawn. You can compare both of the predictions from both of the runs using the weights and biases table. Then one of the cool charts that weights and biases provide is parallel coordinates chart. So I will quickly switch to another project because there's not much to see in this parallel coordinate chart as there were very much less parameters to tune. So recently I did a project where I had to tune a lot of hyperparameters, and weights and biases provide their own hyperparameter tuning engine, which is called weights and biases sweeps. So you can use sweeps to automate your hyperparameter tuning. And so this is the dashboard that is being created. I will quickly show how you can create such dashboards. So first, you have to define a sweep config. So sweep config is you can define it in a dictionary format or even in YAML files if you are running through scripts. So you have to define the method that you are gonna use for sweeps. So here I am using random method, but weights and biases also provide grid and Bayesian search. Then all the parameters and all the distribution from where the values of the parameters should be sampled from. So if you have any non-changing parameter, you can just denote it via values. And for example, here I'm saying batch size should come from a categorical distribution, and these are the values that the batch size should take. So similarly, you can look up more about the distributions. There are many distributions available on the documentation like log uniform, int uniform, etc. Then we define the sweep config, and then we just define a single function where all the training will happen, and we just initialize the agent using sweep command, and it creates a sweep ID. It is a unique ID per sweep you perform. And then you can just automate the whole process of hyperparameter tuning by calling the agent command and giving it the sweep ID. The interesting thing about is suppose if you are having 4 machines and you wanna perform perform the same sweep on all the 4 machines. So what you can do is take the same sweep ID and run the sweep on all 4 machines, and all the 4 machines sweep configurations will be synced up on the agent. Weights and biases agent will sync all of the communications between all those 4 servers. So you can scale up this hyperparameter tuning to as many machines as you like. So that's the interesting thing of it. And so after running the sweep, you can see this dashboard. So for each sweep, you can have a single dashboard, and this chart shows how the runs were, how the accuracy was there on a particular timestamp. So we can see how the accuracy developed over the timestamp for each timestamp. Then this is the parallel coordinates chart. So each line in this parallel coordinate chart denotes what was the configuration used. So for example, for the highlighted one, it was batch size 24, then learning rate of 0.0001, and so forth, and the final metric value which you are interested in. And this parameter important chart is basically a random forest model which weights and biases trains inside the browser to tell which parameters are having the most positive or negative impact on your the metric of your choice. So you can see that here the batch size is negatively correlated. So probably we should use lower batch sizes to get higher accuracy. And now the interesting thing is that you can even select a subset of runs to analyze, and this is updated dynamically on these only these selected runs. So that's a pretty good feature. As you can see that for these this parameter important chart is only for these runs which are being selected inside this box. So you can analyze whatever the range of runs you want to analyze. And so yeah, that's it from me.
This concludes today's community panel focused on Built with W&B. A big thank you to both Andrada and Atharva for presenting their use cases.